So my goal for today is to cover the high frequency response of the common base amplifier, as well as look at the open circuit time constant approximation. And then once we wrap that up, we will be done for today. So I'm going to start by drawing our circuit of interest with all of our coupling and bypass capacitors shorted out. Okay. So here is our resistor R1. Here is our resistor R2. My base capacitance is shorted out, which is going to put my base directly at ground. And so that means that from our small signal perspective, resistors R1 and R2 are shorted out on both sides, so they're not going to show up anywhere. Okay. Here is my resistance RE. My resistance R sig. And then here's where I'm applying my input voltage. Here's my resistance RC. And then with C out short circuited, the resistance RL will be between my collector node and ground. And I'm going to put my V out terminal here, right? So this is what my circuit looks like with all of my coupling and bypass capacitors short circuited. Now I'm going to put in my high frequency capacitances. So I'm going to have one high frequency capacitor placed between the base and the collector. So this is our capacitance C mu. I'm going to have a high frequency capacitor placed between my base and my emitter. So this is C pi. And then I'm going to have a capacitor placed between my collector and ground. So this is CCS. Our midband gain for this system is going to be the same thing it was at low frequencies, which would be GM R naught in parallel with RC. So it's our goal to kind of extract that out of things. And in a moment here, I'm going to draw my small signal model, but I want to look at this circuit first and kind of see what simplifications I might be able to make. So for example, my capacitor C mu is between the collector terminal and the base terminal, but because my base is at ground, that's going to make C mu appear as if it is in parallel with that capacitance CCS. So I could really just lump those together, right? My capacitance C pi is between my emitter node and ground. So I'm going to put that in parallel with my resistance RE. And so my small signal model, my first pass at my small signal model, because we're going to simplify this. Should look something like this. Okay. So here's my base terminal at ground, once again with my bypass capacitor CB appearing as a short circuit. R1 and R2 get shorted out. So here's R pi and VBE. Here's GM VBE in parallel with R naught. Here's my collector node. Between my collector node and ground, I should have a resistance of RC in parallel with RL. So I'm going to put that here. And between my collector node and ground, I should also have that capacitance C mu and CCS. And I'm just putting those as if they're adding those values together because capacitors in parallel combine that way. And then here's my output node. Now, looking at my emitter node, I'm going to have a resistance R sig, and I'm going to apply my input voltage Vn here at this terminal of R sig. The other terminal of R sig is connected to my emitter. And then between my emitter and ground, I should have that resistance RE. And then between my emitter and ground, I should have a capacitance C pi. So before we make any modifications to this guy, how are we feeling about this representation? Anything seem odd or untoward? All right. So in order to simplify this guy right here, I'm going to make a couple of observations. The first of which is I should see some total impedance connected between my collector and ground, which would just be the parallel combination of RC, RL, C mu, and CCS. So I can lump all those together as a single impedance. My resistance RE is between the emitter node and ground. My capacitance C pi is between the emitter node and ground. And my resistance R pi is between the emitter node and ground. So I'm going to lump all three of those things together and call that an impedance Z pi, okay? So making those simplifications, our circuit now looks something like this. So I'm just going to call this impedance Z pi, over which our voltage VBE occurs. Here's GM VBE. R naught. ZC. V out. R sig. And Vn. So I can kind of break this thing down into two stages, like so, where everything up above here is my amplifier stage, and everything down below is my input stage. Where, just to be clear here, my input stage is just going to be a voltage divider, where I'm going to have R sig and then the impedance looking in to the emitter node. So if I applied my input voltage directly to the emitter node, what would this look like? just a simple common base amplifier that has a gain of GM times R naught in parallel with ZC, right? Then I have that input stage looking in to that emitter node. I would have a resistance of effectively Z pi in parallel with 1 over GM. So putting those two things together, and by the way, that is the approximation where we're saying that early effect isn't going to have any significant impact like we've done for every other input stage, just to make the math less terrifying. So overall, our frequency dependent voltage gain for this system, AV of omega, which would just be V out over V in, is going to look something like Z pi in parallel with 1 over GM divided by R sig plus Z pi in parallel with 1 over GM. So this is from my voltage divider input stage. And then that quantity is going to be multiplied by GM R naught in parallel with ZC. Let's define a couple of things here really quickly. Z pi is nothing more than R pi in parallel with RE in parallel with 1 over S C pi, which is just R pi in parallel with RE divided by 1 plus S R pi in parallel with RE times C pi. And ZC is RC in parallel with RL in parallel with 1 over S C mu in parallel with 1 over S CCS. And I can express that as RC in parallel with RL divided by 1 plus S RC in parallel with RL times C mu plus CCS. And to make the algebra a touch easier, I'm going to call this bit right here RC prime, and I'm going to call this bit right here CC prime. So that's just the total resistance connected between the collector and ground, and the total capacitance connected between the collector and ground. That's going to make the algebra less horrifying when I rearrange things. Yes, sir.
Did it say that you can add them in the first?
We did. So I added them together, CMU and CCS.
And then ZC has been in parallel?
They were in parallel to begin with.
Okay, yeah, we're bringing it back. Okay.
Yeah.
Sorry.
Yeah. Just, I want to be clear here. CCS is between the collector node and ground. C mu, so here's the collector node, here's ground. C mu is between that same collector node and this ground over here. So they are definitely in parallel. And I know that I can just add the capacitances together because they're in parallel, and then take the impedance of that equivalent capacitance, which is effectively what I was doing here. All right, so let's manipulate the GM R naught in parallel with ZC bit first. Okay. So GM R naught in parallel with ZC is going to look like GM times R naught times ZC over R naught plus ZC. And from here, this is going to look like GM multiplied by R naught times RC prime over 1 plus S RC prime CC prime. So what I'm going to do down here in the denominator is I'm going to multiply that R naught times 1 plus S RC prime CC prime over 1 plus S RC prime CC prime so that I have a common denominator in my denominator so that I can lump everything together. Okay. So that'll be R naught times 1 plus S RC prime CC prime plus RC prime over 1 plus S RC prime CC prime. Are we all okay with the algebra that happened there? I just multiplied that R naught by a factor of the denominator over the denominator so that I can lump them together. The RC over 1 plus RS RC prime CC prime is just ZC. So I have the same denominator in my numerator and my denominator. I know that's an odd sentence, but those guys are going to cancel each other out, and I'm left with this thing right here. So I'm going to have an R naught. So I'm working on the denominator first here. So the R naught is from the R naught times 1 plus S RC prime CC prime. I'm also going to have an RC prime by itself. That's from the right-hand side. And then I have my S times R naught RC prime CC prime. So is everybody okay with that as a denominator? And then my numerator is just going to be R naught times RC prime. And so what I'm going to do now is I am going to pull out a factor of R naught plus RC prime from the denominator. So that's going to look like R naught plus RC prime times 1 plus S times R naught RC prime CC prime divided by R naught plus RC prime. Here I have R naught times RC prime, like so. Let me make this bracket large enough to take everything it needs. Are we okay with this? Algebra itself. So it seems pretty obvious now that I can pull out an R naught times RC prime over R naught plus RC prime, which is just R naught in parallel with RC prime from this thing. Times 1 over 1 plus S R naught RC prime CC prime divided by R naught plus RC prime. And so now effectively I just need to figure out how to get rid of the RL that's buried inside of the RC prime, and this will be in exactly the form that I want, right? So that's going to look like GM R naught in parallel with RC times RL divided by R naught in parallel with RC plus RL. So that's me pulling that RL out of that R naught in parallel with RC prime times 1 over 1 plus S R naught RC prime CC prime divided by R naught plus RC prime. And so that's my final result for effectively what the amplifier stage is doing. When I've got my mid-band gain pulled out, this term right here comes from the fact that RC is in parallel with RL, so I had to do a little bit of manipulation to just get it looking like R naught in parallel with RC. And then this bit over here tells us where our pole is going to come from, right? So we should see that our first pole of this system, so this would be omega p h1 is negative R naught plus RC prime divided by R naught times RC prime times CC prime, or negative R naught plus RC in parallel with RL over R naught times RC in parallel with RL times C mu plus CCS. So now we can manipulate the input portion of our system's transfer function. So that's the Z pi in parallel with 1 over GM divided by R sig plus Z pi in parallel with 1 over GM. So starting with our kind of base quantity described above, this is going to look like Z pi times 1 over GM divided by Z pi plus 1 over GM divided by R sig plus Z pi times 1 over GM divided by Z pi plus 1 over GM. And so I'm going to multiply this R sig by Z pi plus 1 over GM divided by Z pi plus 1 over GM to once again have a common denominator in each of the denominators of my ratio here. And so this will be good. So I'll have Z pi times 1 over GM divided by Z pi plus 1 over GM all over R sig times, excuse me, Z pi plus 1 over GM plus Z pi times 1 over GM all over Z pi plus 1 over GM. the denominators of both functions, or the numerator and the denominator cancel out. And so that leaves me with z pi times 1 over gm divided by r sig times z pi plus 1 over gm plus z pi times 1 over gm. And I'm going to multiply this by gm over gm, which, if I did this correctly, and I hope I did, would give me z pi divided by r sig times 1 plus gm z pi plus z pi. James, you're nodding your head like I did this correctly, so I'm going to assume that we are both right. Okay. So now what I'm going to do is I'm just going to distribute that r sig and effectively factor out a z pi. So let me write that down. So the z pi in my numerator is going to stay the same. Now I'm going to have an r sig. So hold off to writing things down in a moment because I'm going to write it all out and then I'm going to factor things out. So I don't want you to have to erase some stuff. So I have a z pi, and then I have a gm z pi r sig, right? So I believe that I can pull out 1 plus gm r sig from everything that isn't the r sig by itself. And so that's going to give me 1 plus gm r sig times z pi. And this will be the easiest form for me to substitute in the z pi relationships and give myself a common denominator and all that kind of jazz that I've been doing. So substituting in for z pi now, we're going to have r pi in parallel with re divided by 1 plus s r pi in parallel with re times c pi divided by r sig times 1 plus s r pi in parallel with re c pi divided by 1 plus s r pi in parallel with re times c pi plus 1 plus gm r sig r pi in parallel with re divided by 1 plus s r pi in parallel with re c pi. And now this denominator cancels that denominator, leaving behind r pi in parallel with re all over r sig plus 1 plus gm r sig r pi in parallel with re plus s r pi in parallel with re r sig c pi. And now we can see where our second pole is going to come from. So omega pH2 is going to be negative R sig plus 1 plus GM R sig R pi in parallel with RE divided by R pi in parallel with RE times R sig on C pi. And that's what our transfer function could look like, putting those bits together, pulling out our midband gain and all that kind of good stuff, pulls and zeros. All right. So now we'll do our open circuit time constant approximation, which we should be able to wrap up in a nice 5 to 10 minute stops, and we'll be done from there. I mean, we got nothing but time. If you want me to wait so you can write this down, we got 45 minutes to cover 10 minutes of material. All right. So open circuit time constant approximation. So I hope this isn't too wild or crazy, but since our capacitor CCS and our capacitor C mu are in parallel, they're going to see the exact same resistance, right? So CCS and C mu will see this. Okay. So here is my base RC in parallel with RL. And then we're looking into this node to find, let's just call it RC mu. So I just want to be clear here, we're doing the open circuit time constant approximation. So the capacitance E pi is looking like an open circuit, which is why it's not showing up in parallel with RE and R sig down there. And the reason why RE and R sig appear as if they are in parallel is because we are sorting out our input voltage. We're just finding the equivalent resistance seen by that capacitor. So what does this look like to you guys? Common emitter amplifier with the generation. The output resistance of a common emitter amplifier with generator, right? Which we've seen before on numerous occasions at this point. So from that, we can say that RC mu is the same thing as RCCS is RC in parallel with RL in parallel with R naught plus R pi in parallel with RE, bless you, in parallel with R sig plus GM R naught R pi in parallel with RE in parallel with R sig. And no derivation because we've done it probably 10 times at this point. Looking into the collector terminal of a common emitter amplifier. Okay. So now let's figure out what C pi sees. So once again, my base is grounded. Here's R pi and BBE. Here's my emitter terminal. My collector terminal. RC in parallel with RL. So between my emitter and ground, and I'm going to choose to put this kind of over here, we have RE in parallel with R sig again, and then here are the terminals where we've taken our capacity out and we're looking at. So I would argue that since RE and R sig are directly in parallel with that capacitor, we're going to see RE in parallel with R sig in parallel with whatever we see looking up into the emitter, right? Well, what we see looking up into the emitter node is just the input resistance of a common base amplifier. So that means that RC pi is just RE in parallel with R sig in parallel with R pi times R naught plus RC in parallel with RL divided by R pi plus 1 plus beta R naught plus RC in parallel with RL. There we go. All right, so what I'm going to do now is I'm going to go to my office and I'm going to reply to the 30 emails I got from you guys to set up the scheduling for the advising and all of that kind of good stuff. Then I am going to put up homework 12 for circuits 2, which should take me literally just a couple of minutes. And then I'm going to catch up on homework assignments for you guys, which I'm sure you're thrilled about. So I'm going to try to make sure that it is things that we have covered in this class and pretty much just direct applications. If it's not a direct application thing, it might be like, hey, for a MOSFET, perform the short circuit time constant method or the open circuit time constant method thing so that I'm not making you just derive a bunch of gross stuff for the sake of deriving it. Because I don't want you guys to suffer through that. You don't want you guys to suffer through that by any stretch of the imagination. So that's what my expectation for your homework assignments are going to be, is just BJTs straight up like we did things, or a MOSFET, and then we're approximating things using the different approximation techniques that we've dealt with. All right. See you guys on Wednesday, where I'm going to try to knock out course, or I guess it would be emitter follower amplifiers in one day. Thank you.